Yeah, thanks for the invitation. It's a pleasure to come here and speak. This is my, basically a summary of my thesis I'll be presenting, so I want to acknowledge my advisor, Mark Kisin, for pointing me in these directions. So the motivation of the study of these moduli spaces of representations and pseudorepresentations is moduli of a profinite group, a Galois group in particular, and how these have been useful in number theory. But first I want to start out with a general non-topological setting. So I'm going to use A to denote a commutative ring, and then R will be an associative A algebra. And eventually we'll be studying group algebras for this. And so for representations, I'll use this notation to denote this set of matrix-valued representations, where B is a commutative A algebra. Just algebra homomorphisms into the d-dimensional matrix algebra. But first, I want to define the notion of pseudorepresentation that I'll be using, which is this notion is used due to Chenevier. And he calls them determinants, but I'm going to call them pseudorepresentations. So a pseudorepresentation, I need this I'll be denoting by D, the dimension. It's the following data. We write DRA for a pseudorepresentation, but it's not merely just this map. It's actually many maps for all commutative A algebras B. It is a map dB, that I'll denote dB, from R tensor B to B, satisfying the following conditions. It needs to be homogeneous of degree D. This means that for any element of B and any element x of R tensor B, that it is indeed homogeneous of degree D. It also needs to be multiplicative for the algebra structures on each of these. And among that, unit preserving. And then finally, it needs to be functorial in A algebras. So for any map B to B prime of A algebras, we have a map dB prime, and we just want this to commute. So this is a pseudorepresentation. And for notation, I'll set for a B-valued pseudorepresentation will be PSR dr B will be the set of pseudorepresentations that are d-dimensional from R tensor B to B. Okay, so we call these pseudorepresentations. How do we get this name? Well, they're related. We'd like to have some relation between representations and pseudorepresentations. And so it turns out we do have a map. Any representation induces a pseudorepresentation, and I'll call this psi box, psi for pseudo-representation. And what it'll do is just send one of these representations to essentially the composition with the determinant. So rho sends R tensor B to MdB, and then the determinant is a homogeneous degree D map. And this gives us its functorial. So whenever you have a B to B prime morphism, you then get, so this would be that tensor P sub B, and this would be, if we make this D, and then this would be dB prime. And we have all this data of a pseudorepresentation. And all right, so now we see we have a map from representations to pseudo-representations. And what data does it have? It basically retains the data of a characteristic polynomial. So given any pseudo-representation, whether it comes from a representation or not, there's a notion of characteristic polynomial. We take our pseudo-representation, and we take the particular function for the polynomial algebra, and just ask where t minus r gets sent to, and define this to be the characteristic polynomial, which I denote by chi. And I give notation for the characteristic polynomial coefficients. It'll look like td plus some, just like a normal characteristic polynomial. And so lambda, this is the d, lambda 1 will be the trace, and so forth. And so we see that when we form a pseudo-representation from a representation, this is the characteristic polynomial of that representation. But any pseudo-representation gives us a characteristic polynomial. And then it turns out that this is, in a sense, all the data it has. So Chenevier showed that these functions, lambda I, where I goes from 1 to d, characterize the pseudo-representation. OK, so this shows how the these pseudo-representations are an update of versions in the past due to Taylor following Wiles, and studied by Roquier and other people. And I'll call these pseudo-characters. And if we just take just the trace function, so I'll call them pseudo-characters because basically they kept track of the data of the trace function, whereas these keep track of all the characteristic polynomials. So there is an induced pseudo-character lambda 1. And this satisfies the pseudo-character identity that these are defined to have. Now, it's known that semi-simple representations over an algebraically closed field are characterized by their characteristic polynomial. And so we get from that, we would get a map from some such representations into pseudo-representations. But in the case that we're working over an algebraically closed field base, not only is that true, but also every pseudo-representation is realizable. So there's a natural bijective correspondence with semi-simple d-dimensional representations of R up to isomorphism. And this is really the fact that says that this notion of pseudo-representation really holds some water. And so you could say out of this that even though I haven't spelled out specific relations among characteristic polynomials, coefficients, although there certainly are many, this pseudo-representation formulation here nicely packages all those relations. Also, these things have a nice moduli theory that when Chenevier defined these was already complete in essence. These pseudo-representations are examples of what are known as homogeneous multiplicative, so homogeneous multiplicative polynomial laws. And the study of these were initiated by Roby, and they're strongly related to the divided power algebra of a module. And from this, so one immediately gets from Roby's theory that this functor of pseudo-representations is representable. There exists a universal pseudo-representation. And to draw that out, I'll draw du. So we fixed the data R, A in the dimension D. There's a universal pseudo-representation of dimension D. And the ring representing this functor is the dth degree filtered piece of the graded piece of the divided power algebra of R treated as a module. So there's a universal pseudo-representation, and you take the Abelianization of that. So this is where the universal pseudo-representation, and because it's homogeneous, I can characterize it by telling you where it sends elements of R to. The multiplication law on this is relatively a little bit hard to explain, but in the case where R is free as an A module, I can make it more concrete. It's just the dth symmetric tensors. And we can see this has a multiplication law, just the coordinate-wise A algebra law on R. And so the pseudo-representation is just given by sending R to R tensor D. So this is a degree D homogeneous. And so now we can say that the pseudo-representation functor is representable by this ring. And I'll just write OPSR for short when everything else is understood. This Abelianization being the maximal Abelian quotient ring. So now we have a scheme that whose geometric points parameterize semi-simple representations. And now, having started these out, I'd like to next look at the geometry. The geometry of this map from representations to pseudo-representations. As long as R over A is finitely generated and A is Noetherian, then all of these schemes that I'll be talking about are finite type. So, for example, this representation functor here is representable by a scheme. Okay, so the situation. Yes?
Can you sort of glue I presume you can. Presume the answer is yes, but is it obvious that you can glue, so suppose we had one on p to the n for all n, you get 1 over cp.
Yes. Yep.
And is that obvious?
It's clear once it's representable, because that would. Yeah. All right. So yeah, you can definitely glue these, and one nice thing is that they're well behaved in all characteristics. Okay. So here, let me just redraw this. So we have a representation scheme. And we see that this is equivariant for the action of basis change, you could say over here, or really what we're going to use is the action of conjugation, of the adjoint action of PGLD on the matrix algebra. It's equivariant when you endow this with the trivial action, because basically characteristic polynomial coefficients are conjugation invariant. And therefore, there should be a quotient that this factors through. And so one of these quotients is the GIT quotient. GLD, which is just the spectrum of the invariant regular functions. And I'll just write for short GIT for this thing. So because it's equivariant, we get a factorization through this map, which I'll call nu. And this is also finite type, given those assumptions. And now let's think of the geometric points here. There are some one fact. So for geometric orbits, by which I mean in the representation scheme, orbits of geometric points. So for geometric orbits, there's some facts. Semi-simple representations and their orbits are precisely the closed orbits. This is due, I'm not sure originally, but to Kraft or Steinberg, depending on the situation. And then there's a standard fact from GIT that for any orbit O, there exists a unique closed orbit lying in its closure. So I'll call it OCL, such that this orbit is closed, and this orbit is contained in its closure. Now, invariant regular functions can only separate orbits whose Zariski closures do not overlap. And as a result, we have that the geometric points of GIT are also in natural bijective correspondence with semisimple d-dimensional representations as a result of these two facts. But we know from before that this is also what the geometric points of the pseudorepresentation scheme parameterize. And one can check that it's not only an equality of sets, but it's induced by this morphism. So these things are pretty close. They have the same geometric points. Concretely, this implies that that nu is a universal homeomorphism. So basically the enterprise that I'm interested in is showing that this is an isomorphism. And the idea behind this would be that the pseudorepresentation scheme is a concrete replacement for the GIT quotient, or complete candidate for GIT. Now, the reason I'd like to replace it is that the pseudorepresentation functor has a very concrete functor of points. But the GIT scheme only has a good functor of points for geometric points. It exists as a scheme, but I don't know what its moduli functor is for non-geometric points. And so we'll see soon that the concreteness is very useful. The thing is that GIT does have a useful universal property. It's the reason that we don't get a moduli functor out of it is that it's a universal property for morphisms out of it, as opposed to morphisms into it. So it would be nice if they were the same, then I'd have both these properties. So the next thing that so the final thing I show sort of in this generality, although I'll improve on this theorem later on, is that I show that that nu is finite. And this does have some nice geometric implications, which I can now explain. And a nice way to see the usefulness of it being finite is to also consider the quotient stack, yes? Oh, sorry, this is a finitely generated algebra. Yeah, I'll specify finite as a module when it's finite as a module. So there's also...
when you say the idea is that it's not an isomorphism.
Yes. Should be or something.
But it's not. You know it's not.
I haven't completely proved that it is, but I suspect that it is.
Is it that they are isomorphism?
Yeah. Maybe not so far as conjecture. I still need to do more calculations, but I can show it in a particular case that I'll get to soon. But even though I can't show that they're the same, it's still very useful that they're very close.
The R here is maybe it
Could be a group algebra.
So finitely generated does rule out Galois?
It would if you're forgetting topology. But then once you consider topology and you have some finiteness conditions that I'll get to the topological case really soon. So another quotient that's useful to think about is the quotient stack. There's only a slight difference between the quotient stack of these two, but because GLD will always have a stabilizer for this adjoint action, I'll just use the p-GLD quotient stack. And concretely, the the moduli groupoid associated to this would be that it sends A schemes X to the data of a rank D squared, OX Azumaya algebra, along with the data of a representation valued, call it curly E, along with a representation into it, and the morphisms being isomorphisms of such data. So we have maps. I'll call this map here psi, and that's the map I will be most interested for the rest of this talk, the relationship between the quotient stack and the pseudo-representation scheme, and I'll call this phi. So phi is a very particular kind of map that has some nice properties. And I should remark that these I'm just using that these hold for any phi from a stack to an algebraic space Y. An example of something satisfying these properties would be any quotient stack of a scheme X by a reductive group, and when Y being the GIT quotient of an affine scheme by a reductive group. So that's a concrete example. Well, that's the generality, but this is a particular example of that. So the properties that this has are some of the following. That the fact, just by definition, the push forward of the structure sheaf is the structure sheaf below. The next one looks very much like a property of an affine, or very much is for schemes, a property of an affine morphism. It's that if you have a map of quasi-coherent O curly X algebras, then basically the push forward functor is almost exact in the following precise sense for all global sections. There exists an N, and there exists a global section of the source such that the nth power is realized. So these first two properties are, for a morphism like this, are define what Alper calls an adequate moduli space, and he has a really nice paper on these. And then he studied these because they're the characterizing properties of the nice relationship between a quotient stack and a GIT quotient scheme. And basically you can say, and we'll see farther down, that these are basically isomorphisms minus representability. They have properties of isomorphisms like this, like an isomorphism of schemes. They'll also satisfy some properties of proper maps and affine maps, and so I'll name those. So the rest of these properties actually follow from 1 and 2. It's universally closed, universally submersive, and surjective. Mm-hmm. Well, the global sections are, let's see, so these two global sections lie in some Y algebra, OY algebra, because OY is the global sections of the structure sheaf above. They are quasi-coherent algebras on that stack. Oh, I'm sorry. Left out a big, sorry. For any surjection, For any surjection,
But again, it doesn't mention why. It's just a property. I could just think of it as a property of X.
Right. Then this property, then you can define y. In this case, then you can define y with this property. You just take the global sections of the structure sheaf of the stack, and that is, take the spectrum of that, that's y. And so these together make what's called an adequate moduli space.
The second property would be concretely what is it used for?
It's sort of like reductivity is to geometric reductivity linear reductivity is to geometric reductivity as this condition is to this condition. So for linearly reductive groups, quotient by linearly reductive groups, you can erase the n. For geometrically reductive groups, you need the n in this situation here. And so Alper's first paper is called Good Moduli Spaces, and there he mostly works in characteristic 0 with linearly reductive groups where you have this kind of condition. His motivation is to study moduli of curves. So the next property is what we've talked about with the closed orbits. If you have two geometric points of your stack, and if their closures overlap, that implies that they're mapped to the same point in y. And finally, this map is universal for maps from x, from curly x, to separated algebraic spaces. So, actually, maybe I shouldn't have put that up quite yet. So that's a quotient property that the GIT quotient has. Now, here's where nu being finite comes in. Because nu is finite, I can then conclude these same properties for psi, which is the map from representations to pseudorepresentations that I'm interested in. You can then say that 1 doesn't hold, but you can get 2. You can get 3, A, and C, where 3 is 3 statements. So you can get 4 for the map psi. That's what we just explained before, but not 5. So soon I'm going to talk about, for example, projective subschemes in fibers of psi. So it's nice to see it's universally closed. And that follows from the finiteness of nu. What does 2 mean for psi? It would just mean replace y with what? Sorry.
Y does not appear. Y isn't in 2.
Okay, so just send. What am I trying to say? Okay, well then no 2. Okay. Yeah, I mean affine, for example, the reason 2 is interesting is that 2 is 2 for a representable morphism means that it's an affine morphism. That actually implies that it's a generalization of Serre's criterion. If I got rid of n. But so the morphism, the reason I'm calling it the property of the morphism is that maybe I'm. Okay. Well, I guess we can just talk about it afterwards. Maybe I'm a little bit confused about it, but the idea is that y is defined as the spectrum of the global sections of the structure sheaf.
So if you replace x by y in that statement, then it would be the same. Is that what you're saying?
Replace x.
Like because the global sections of, or I mean the sections of y b are the same as the sections of x b. Is that what you mean?
Sections of y. Well, b is only defined over well, it is defined over y. Yeah. All right, let's just talk about it afterwards. There's plenty to get to. So I want to talk about the concrete usefulness of this the usefulness of the concreteness of this moduli functor. And the major thing I'm going to use for that today is the Cayley-Hamilton ideal. So the idea is that when you have a pseudo-representation, we get to each element r, we get a characteristic polynomial, chi rt, but it may or may not be the case that chi rr is 0. It's sometimes not. And it's a useful property to have. For example, whenever you have a representation, and then you take its determinant, so you get a pseudo-representation. Then it turns out there exists an ideal CHD. So right now I'm just saying that D is det composed with rho. And this ideal is it's basically the smallest two-sided ideal such that the pseudo-representation factors through it, and everything satisfies its own characteristic polynomial. We take this quotient. So in particular, this means that any representation will factor through it because by the Cayley-Hamilton theorem, everything satisfies its own characteristic polynomial. So now that we've done this in this particular case, we can apply this idea universally. Basically the same thing that I just did, but with the universal pseudo-representation. So we define the universal Cayley-Hamilton algebra to be the quotient of the tensor product with the pseudo-representation representing ring by the Cayley-Hamilton ideal of the universal pseudo-representation of dimension D. So I call this the universal Cayley-Hamilton algebra of degree D. And from what we just discussed, then whatever with either representation functor, these representation moduli spaces are the same. Because every representation will factor through it, and any representation of the Cayley-Hamilton algebra gives us a representation of R. So there's an interesting result that follows from this. Assuming that we do have this A being a Noetherian ring and R finitely generated, then EDU as an OPSR algebra is finite as a module. Now, if it was a commutative algebra, we'd quickly see that this is the case because it's integral over OPSR because every element satisfies its own characteristic polynomial. It's also finitely generated over a Noetherian ring. However, in the non-commutative case, this does not imply that things are finite as a module as it does in the commutative case. The key idea is that it's integral of bounded degree. And this implies that it satisfies a polynomial identity. A polynomial identity just meaning that there is some polynomial in some finite number of variables, such that when you plug in any tuple of elements from your algebra, you get 0. So an example of a polynomial identity ring is a commutative ring. A commutative ring. In a commutative ring, everything satisfies the identity xy minus yx. And using polynomial identity ring theory, I'll just write pi ring. You can then conclude you can then conclude that it's finite as a module. The polynomial identity ring theorem was developed by like Jacobson and people. They wanted to see under what conditions they could prove some things of non-commutative rings that they proved for commutative rings, and in many cases, a polynomial identity is necessary. Now, the interesting thing that comes out of this is that this means that, yep.
Were you saying that it's a theorem that there's a representation of our modulo, this Cayley-Hamilton ideal,
Yeah.
whenever you start with this? That's a theorem.
Yeah. If I define D in this case as coming from that, it would factor through.
Oh,
if I take the pseudo-representation, I mean, it's
oh, I see. But it's not a theorem about the existence of a representation given a pseudo-representation.
no, it's not. Yeah. Just that if there exists a representation, then it factors through it. So the interesting result of this is that this means that as long as you have a finitely generated algebra over an Euclidean ring, any representation sort of factors through an algebra that's finite over its center, which is an idea that we'll be using later. So now I'll get to the profinite topology. So I'll use gamma for a profinite group. And I'll be talking about the completed group algebra and continuous representations of that. So I'll basically be using ZP in place of A, although I could do it a bit more generally. And now, similarly to before, I'll use curly R, or curly rep, to denote continuous functors of continuous representations, or groupoids of continuous representations. And I need to say on what, so these are groupoids on the appropriate coefficient rings, and for that I'll use admissible ZP algebras. Admissible ZP algebra just being a pro-discrete ring where each of these transition maps have nilpotent kernel. So for example, a polynomial algebra over Fp is an admissible ZP algebra. And a restricted power series ring over ZP is an admissible ZP algebra. Let's see, I think arbitrary diagrams, but I'll limit myself to things that are topologically finite type in what follows. So that'll be workable with the integers. So these are the rings that I work on, and basically when we go to the formal scheme level, these are just the affine ZP formal schemes. So formal schemes over SPIF ZP. Okay, and then also we have a continuous pseudo-representation functor. I won't make it curly. I'll just always assume it's continuous pseudo-representations for this group. And with the definition of continuous pseudo-representation just being that the characteristic polynomial functions are finite. Okay. So the characteristic polynomial functions were these, characteristic polynomial coefficient functions, lambda di, are maps from the group algebra to the ring, and these have to be continuous in order to call the pseudo-representation continuous. Oh, sorry. I just wrote finite. Continuous. So, now Chenevier studied the situation for pseudorepresentations, and he showed that working in this category, that the pseudorepresentation functor is representable. And actually, also not only that, but that it's representable and it's semi-local. Basically meaning that the underlying scheme is a set of points, finite field, spectrums of finite field, and that the pseudorepresentations consist of deformations of these residual pseudorepresentations. So it is semi-local, consisting of deformations of residual pseudorepresentations. And these, I'll just denote those by d bar. So pseudorepresentations of gamma just consist of deformations of finite field valued pseudorepresentations. That's the set of residual pseudorepresentations, and I'll denote that deformation functor by PSR d bar. And R d bar for the local ring that represents those. For notation, its maximal ideal will be M d bar with residue field F d bar, and the universal deformation pseudorepresentation, I'll write du d bar. Now, so even over at arbitrary admissible CP algebras, this still works for, it's still representable by the semi-local formal scheme. Now, as a result, you can then break up the continuous representation functors into the fibers of psi over over each of these components. So we can study these a component at a time. So I'll just say that the representation scheme is the sum, and these actually happen to be the connected components of each of the schemes, whether they're framed or not. Not defined, but so now I can just study each individual fiber over each of these components. Now, there's a finiteness condition that will be useful, and I'll call it phi d bar. And basically, what the definition of this is that to this residual pseudorepresentation, I can possibly, after extending the finite field, I'll get the associated semi-simple representation, semi-simple residual pseudorepresentation corresponding to that finite field valued pseudorepresentation. And the finiteness condition is that the continuous group cohomology of the adjoint representation is finite dimensional. So this is a natural thing to appear because this controls the size of the deformations of this representation. So under this finiteness condition, I show that the deformation ring is Noetherian complete local ring. Chenevier had done this for p being greater than d. Evier. And I definitely, there's a strong use of the polynomial identity ring theory in this. And then the main theorem I want to state about psi bar, I'd like to show that each of these components are representable. But under this finiteness condition, I can show more than that. So I'm studying the map psi bar, or no, just psi to each of these, or psi box to each of these deformation spaces. So the theorem is that not only are these continuous representation functors representable, but they're actually algebraizable by a finite type scheme under this finiteness condition. So the statement is that if you assume this finiteness condition, that this is algebraizable by a finite type spec RD bar algebra. And what this would mean is that there's some finite type scheme or algebraic stack such that if I take its p-adic completion, I get the formal scheme here representing these functors. And just to give a sketch of the proof, the Cayley-Hamilton quotient plays a large role. So you take the completed group algebra and take the quotient by the Cayley-Hamilton ideal for the universal deformation of that pseudorepresentation. And what I can show is that on the assumption of phi d bar, that ed bar is finite as a module over Rd. So it's an Rd algebra. I should say that the Cayley-Hamilton ideal is a closed ideal. And its native topology, so its native profinite topology as a quotient is equal to its p-adic topology. So that's the key result. And then, so now I have a finite Rd module. Well, I have an algebra that's finite as an Rd module. And now you can show that if you take this continuous functor, to specify it, I'll include gamma there, framed or not. We know from the things on the fact that every representation factors through its Cayley-Hamilton algebra, then gives us that this is the same as the representations of the Cayley-Hamilton algebra. And then, just using this module finite algebra over Rd, I can compare this to not the topological version, but the non-topological version of Ed bar with pseudo-representation lying over over Rd. And then because of this fact that it's finite as a module and its native profinite topology is the p-adic topology, then whenever I take in any of these admissible ZP algebras and just consider the values of this functor with no topological restrictions, they're all already continuous. So if I take this finite type, so this is finite type over spec RD bar, but if I take the MD-adic completion, then these are isomorphic formal schemes, or formal algebraic stacks. Okay. So now I can apply, having done this, I can apply any of the results from my non-topological case that apply here under completion. So for example, things being universally closed and so forth. Now the next thing I want to, now that we've done this, I want to basically study psi, but locally on the base. So the results that I'm going to get into now are valid whenever the pseudo-representation scheme below is a complete local ring. Fortunately, that covers all the cases when we're talking about a profinite algebra with this condition. So one of these results is that, so I'll continue using the same notation of, I can basically consider representations of ED bar, which is an algebra over RD bar. So in this case, when the semi-simple representation, FD bar valued representation, corresponding to the pseudo-representation D bar, has distinct Jordan-Holder factors. Then I can conclude that this map nu from GIT to the pseudo-representation scheme is an isomorphism. And, oh, sorry, I need one more condition. When it has multiplicity-free Jordan-Holder factors, and I also need p greater than 2d. As a remark, I don't think this is a fundamental condition. This is because I use Bailliache and Chenevier's technology of generalized matrix algebras here, but I haven't yet updated that theory to work with pseudo-representations instead of pseudo-characters. So that's all that this condition comes from. When p is greater than 2d, I can conclude that they're the same. So I can show so more broadly, when it's not just a complete local base, pseudo-representation base, over the locus of multiplicity-free representations, where the associated semi-simple representations have distinct Jordan-Holder factors, I can say that these actually are, that nu is an isomorphism there. Now this generalizes the case of having one Jordan-Holder factor, which was the absolutely irreducible case that was already well known. So just to sort of draw a vague picture of psi here that I'll draw more clearly in a moment. When d bar is absolutely irreducible, just meaning that rho s d bar is actually simple, then psi is an isomorphism, and this is a result due in the pseudo-character. I guess, well, Chenevier proved this for pseudo-representations and pseudo-characters in the appropriate characteristic. This is due to Mazur and Carayol, who showed that a deformation of a absolutely irreducible representation is characterized by its trace. And then Roquier and Nissen, who showed that any deformation of a pseudo, of the pseudo-character associated to an absolutely irreducible representation is realizable as an actual representation. In general, so for general d bar, you have our complete local ring of pseudo-representation scheme, but there's a locus on which it sort of corresponds to reducible representations, and that can be made rigorous. And then over this locus, there's positive dimensional components. I'm sort of drawing it like a blow-up, and Belaïch and Chenevier have actually used to their advantage the idea that it ought in some ways to be comparable to a blow-up, even though, well, I mean, it is non-representable, but certain projective parts can be comparable. For concreteness now, I want to give an example of some of the geometry that we see appearing here more precisely than that. I want to give an example where we take the absolute Galois group of QP, and we take d bar to be the determinant of the cyclotonic character mod p plus the trivial one-dimensional representation. And what I want to give is a picture of the of psi of the special fiber of psi here. So to figure out this picture, first we need to know what representations have this particular characteristic polynomial, and these will be extensions.
This is the same p as we had a minute ago.
Yeah. Or, yes. So we know from local Tate duality that as long as p is greater than 2, the dimension of this extension space is 2. Now, this means that if I take E1, E2, E3 be a basis of cocycles, so not cohomology class, but cocycles, those are exactly the ways to fill in this upper corner here. So I could get a positive dimensional family. So this would be like a positive dimensional family over A3, and this would actually define a map into the special fiber of the framed moduli space. But I want to consider these things up to isomorphism. The way that we get down from 3 dimensions to 2 is the cohomology classes, and that corresponds to the action of the unipotent subgroup of the Borel of PGL2. I've already sort of put these representations in this form, and I wanted to consider them up to isomorphism. So all I have left to act by, once I put them here, is the Borel of PGL2. Acting by the unipotent subgroup brings me down to this space, but then all that's left is the one-dimensional torus. So as a result, what I get in this fiber, and I'm drawing the picture of this fiber, is the projectivization of this X space. So this is a P1. But there is the semi-simple representation. That's the 0 in this vector space. And so all of these, this is just the standard construction of a projective space out of affine space minus the origin. All of these points are open, and then this is the one closed point in this fiber. It's the semi-simple representation. And it has an extra stabilizer of a GM, whereas every other point has no stabilizer. Now, these are upper triangular representations. All I need to do is consider the lower triangular ones. So for extensions in the other direction, the dimension is 1 as long as p is greater than 3. So now the rest of the picture is that I get a p naught from that lower triangular extension. So just a point, but then this is an open point, and there's the closed point. It's just A1 mod GM. And so to finish, I want to give a generalization of this phenomenon. Oh, they were a basis for the cocycles. So this is, yeah. And so each cocycle is that space of cocycles is all the ways to fill in this upper right corner. Yeah. So we see that there's these projective spaces appearing, and the picture isn't usually nearly as simple as this. But it turns out the final idea I'll give is that there's notions of stability that give rise to these projective spaces. And not only that they appear in the special fiber, but I can also keep track of an ample line bundle so that they deform to make. So I'll state the theorem. So given a residual pseudorepresentation and theta, which is a notion of stability that I'll define in a bit, satisfying certain conditions, which I'll explain in a moment. So there exists a spec RD bar projective fine moduli scheme of representations. So that I'll denote this by rep S for stable d bar theta, and this will be immersed into the whole space. Okay. So we've seen the special fiber of such a thing over there, and I want to just give the general recipe. So the recipe, in order to give the recipe, I just need to work with the special fiber. So I'll write the reduction to the special fiber of the Cayley-Hamilton algebra as E bar. All right, and this is a finite dimensional algebra over f d bar. And now this theta is a character, integer value character of the Grothendieck group of the representations. So this being finite dimensional algebra, it's a finitely generated abelian group. You can take the simple representations as generators. And given this character, I can give a definition for whenever I have a E bar representation M. I say that M is theta semi-stable. So this is just a generalization of the notion of stability and semi-stability for a vector bundle on a curve. I'll write theta SS when theta of M is 0, and for all sub-representations, theta of M is non-negative. I'll call it theta stable when, again, theta of M is 0, and for all sub-representations, it's strictly positive. Theta of it is strictly positive. So where theta of a representation, we just take its image in the Grothendieck group. Basically, it's semi-simplification, and then look at what the character adds up to. So I need a certain condition on these two relative to each other. So these are the following conditions. Firstly, theta needs to be indivisible on, yep. Yeah.
Representations of E over F.
Yes.
What was E? E would be D bar.
E bar.
Oh, E bar.
Sorry, everything's E bar here. Sorry if I missed it. Just working on the special fiber for all of this. So the first condition is that whatever simple components, say that there are 3 of them without multiplicity, appear in the decomposition of the semi-simple representation corresponding to d bar, you just want these sent to a vector where the GCD of these numbers is 1. That's all that indivisible means. Otherwise, you could just reduce it to such a thing. The next condition is just a non-triviality condition, that theta of this particular semi-simple representation is 0. This is important because the entire space of representations, rep d bar, is exactly those representations whose semi-simplification is this. And we want these spaces to be, of semi-stable things to be non-empty, so we need this condition. So that's just non-emptiness. And finally, this is really the only interesting condition. It's that if the semi-simplification is of some of this E bar is this residual representation corresponding to the pseudo-representation, then theta semi-simplicity implies theta, theta semi-stability implies theta stability. So I just want to give one example to conclude and see one of these spaces. So let's say that the semi-simple representation has this decomposition.
Do such things exist?
Yeah, I'll give an example right here.
But they always exist still?
Given a theta and d, that's not necessarily the case.
No, but given a d, is there always a theta?
No. For example, if it was just, if the semi-simplification was rho 1, there you'd have trouble finding a non-trivial thing satisfying that. So here's one example where you can find it. So that rho 1 to rho n, possibly with multiplicity, be simples, but let rho n be distinct from the rest. And now define theta on these simples as follows. 1 for the first n minus 1 of them. And rho n being sent to minus n minus 1. So this will actually satisfy all three of these properties. Now, the representations that we end up finding in this projective moduli space are exactly those which, well, they can have anything going on. It could be extensions in either direction. It could just be semi-simple in here. But all of these extensions here have to be non-split. For this particular theta, theta semi-stability is equivalent to theta stability, which is equivalent to rho n being the unique simple quotient. Now, on the special fiber, this result is entirely due to King, he got interested in it from moduli of quiver representations. Translating it to just the general finite dimensional algebra over a field is straightforward. And the work I had to do is just to track the ample line bundle through these equivalences and make sure that I could deform it. So that I could get a projective space over RD bar, as opposed to, you could just quote his theorem to say that these projective spaces exist in general. The final thing I'll mention is that I also, yep.
So the assertion is in this case that theta semi-simplicity is the same as, semi-stability is the same as theta stability for any
one of them.
You're not just ones with the same semi-simplification.
Sorry, this was, it was just supposed to be for these ones. So if.
You're just verifying the last condition, as it were.
Yeah, I'm requiring this condition. If you don't have that third condition, then there's a quasi-projective space, of quasi-projective fine moduli space. But because there's in that case, once you go to the cusps, it may not be a fine moduli space anymore. But if semi-stability is the same as stability, then this works. And the final result I'll mention is that in the case of representations of a local field, I generalized a result of Kisin, just showing that giving loci for which p-adic Hodge theory conditions hold, basically generalizing it from the case where A is a complete Noetherian local ring. In other words, it's a quotient of this kind of ring. And I just generalized it to adding on perhaps some restricted power series. I just repeated Kisin's technique, and there are some things I had to generalize. Yeah, in this order. But are you asking about the other order? Yeah, this order. So I can verify. So I did this case, verifying that there exist loci inside of a characteristic zero fiber satisfying conditions from p-adic Hodge theory, such as crystalline with bounded weights and more general conditions. And I just want to point out that one case where this arises is if you're considering a moduli like a family of extensions of two crystalline representations, say, and if this moduli space, if this family, we ask which elements of these families satisfying a certain condition, this generalization would be necessary because it may be the case that not all of these representations have this lie over the same residual representation. So having positive dimensional families such that it is appear as representations is necessary. So my result would just be that if you apply one of these conditions, that this loci would be Zariski closed in such extensions. Mm-hmm. Yeah, basically the same conditions from Kisin's potentially semi-stable deformation rings. Sorry?